Electronic configuration of atom. Each of the orbits can accommodate a fixed number of electrons, and maximum number of electrons in an orbit is equal to 2n square, where n is the number of orbit. You know there are 4 orbits named as K, L, M and N. K is given number 1, L is number 2, M is number 3 and N is number 4. Now if you want to find out the maximum number of electron in K orbit, then you can use this formula 2 multiplied by whole square of 1 give rise to 2. In case of L, that is 2 into 2 square, that is 8. For M, 2 is 2, 3 square, that is 18. And for 4, 2 into 4 square, that is 32. So K shall have maximum 2 electrons in that, L shall have maximum 8 electrons, M can accommodate maximum 18 electrons, and N orbit can accommodate maximum 32 electrons. In the outermost shell of any atom, the maximum possible number of electrons is 8, except in the first shell, which can have at most 2 electrons. And this is also known as the rule of Tate. We can say there can be maximum 8 electrons in outermost shell of an atom. The arrangement of electrons in different shell is known as the electronic configuration of element. We can define electronic configuration as arrangement of the electrons in different shells is known as electronic configuration of an atom. The pictorial representation of Bohr's model of hydrogen, helium, carbon, sodium and calcium atom having 1, 2, 6, 11 and 20 electrons will be shown as, we will see here how to fill up the electrons and how to make a pictorial diagram of that atom. So first of all, we take example of hydrogen atom. This is nucleus, and around nucleus there are shells. So first of all, there will be shell K, in which only one electron will reside, because hydrogen have only one electron. Now if you draw the diagram of helium atom, then it will be nucleus and is surrounded by different energy shells. You know that atomic number of helium is 2, so there are 2 electrons in K shell, like that. For carbon atom, atomic number is 6, so you can draw here a nucleus. Around nucleus there are, so we know that there are some shells which surround the nucleus. This is K shell, and above K shell there is L shell. So first of all, you know that in K shell there should be maximum 2 electrons, and we have 6 electrons, so rest 4 electrons will be filled up in L shell. Now we can draw the diagram for sodium atom, and the atomic number of sodium is 11. So first of all, draw the nucleus, and like that there are energy shells. first of all, there is K shell and can have maximum 2 electrons. Then L shell can have maximum 8 electrons. So there are 10 electrons and remaining 1 electron will goes to M shell. So there are total 11 electrons. So now we can here set up an electronic configuration for each atom. Here, so here for hydrogen atom there is only 1 electron, so configuration is 1. For helium atom there are 2 electrons in same shell, so configuration is 2. For carbon atom there are 1, 2, 3, 4 and 2. So 2 electrons in K shell and 4 electrons in L shell. And for sodium atom there are 2 electrons for K shell, 8 electrons for L shell and remaining 1 electron for M shell. So configuration of sodium is 2, 8 and 1. Now if you want to draw the pictorial diagram for calcium atom, so first of all find out the atomic number of calcium, that is 20. Now nucleus, around nucleus there are some energy levels. Is M. Now we fill the electrons. You know in K shell there are maximum 2 electrons. In L shell there are maximum 8 electrons. 4, 5, 6, 7, 8. In L shell there can be maximum 18 electrons, but we have studied earlier that in a shell can accommodate maximum 8 electrons. So in that shell we can fill 8 electrons like that, 7, 8, and the remaining 2 electrons will be outermost shell, because a shell can have maximum 8 electrons, so remaining 2 electrons will goes to outer shell. So configuration of calcium atom like that, 2, 8, 8, 2. Here 2 electrons will be in K shell, 8 electrons will be in L shell and 8 plus 2 electrons will be in M shell. Now here you can ask what is the requirement of filling the 2 electrons in outermost shell, and we know that M can have maximum 18 electrons, so why not the configuration should be 2, 8 and 10. So there is some reason behind this. These shells are further divided into subshells like that. Shells are divided into subshells. The K shell have S subshell, L shell have S and P, M have S, P and D, and N have S, P, D and F. And there are maximum electrons found in each subshell. S can have 2 electrons, P can have 6 electrons, D can have 10 electrons and F can have 14 electrons. So if you count in K shell there are only S orbital, so total electron in K will be only 2. In L shell there are 2 subshell S and P, and we know that S have 2 electrons and 6 can have 6 electrons, so total S plus P give rise to 8 electrons. In M shell there are 3 subshell S, P and D, and S have 2 electrons, P have 6 electrons and D have 10 electrons, so total are 18 electrons. And in case of N there are 4 subshells S, P, D and F. If you sum all the electrons then it comes to 32 electrons. Now if the outermost shell has 8 electrons, it is said to be an octet. If there are 8 electrons in outermost shell, it is said to be an octet. And if there are 2 electrons in outermost shell, then it is said to be a duplet. Now here we can see electronic configuration of elements up to atomic number 30. So we can see here some examples of electronic configuration. So we will see the first of all atomic number, then symbol of element, then name of element, then electronic configuration. Here we will see atomic number of 5, atomic number of 11, atomic number of 19, then atomic number of 21, 29 and 30. The symbol of atomic number having 5 is boron, B, and name is boron. The element which have atomic number 11 is nothing but sodium, and symbol of sodium is, you know, that Na. The element which have atomic number 19 is potassium, and symbol is K. The atomic number element have atomic number 21 is scandium, symbol is Sc. And the element have atomic number 29 is copper, and its symbol is Cu, and at last it is zinc. Now electronic configuration of atomic number 5. So first of all 2 electrons in K shell, then 3 electrons in L shell. So there are 2 plus 3 gives us to 5. For sodium there are 11 electrons, so 2 electrons will be filled up in K shell, 8 electrons in L shell, and remaining 1 electron in M shell. In case of potassium, 2 electrons in K shell, 8 electrons in L shell, again 8 electrons in M shell, and again 1 electron in M shell. So there are 2 electrons in K shell and 8 electron in L shell and 8 plus 1 electron in M shell. In case of scandium, 2 electrons in K, 8 electrons in L shell, then 9 electrons in M shell, and remaining 2 electrons in M shell. For copper, the configuration will be 2, 8, 18 and 1. And for zinc, this is 2, 8, 18 and 2. So here we can see some examples of electronic configuration. For boron, it's very easy, 2 plus 3 gives us to 5. For sodium, it's 2, 8, 1. But in case of potassium, scandium, copper and zinc, there is some ambiguity. In potassium, we have filled only 8 electrons in M shell, but it can have maximum 18 electrons. But here we will see that the last electron will go into S orbital. That's why this orbital can have 8 electrons and this will have 1 electron. So rest elements are follow this path. Earlier we discussed about subshells, which are the part of the shells, and now we define an orbital. An orbital may be defined as a region in the 3-dimensional space around the nucleus where the probability of finding an electron is maximum, and the maximum capacity of each orbital is that of 2 electrons. Here we have seen S orbital first of all, and you know that S orbital have maximum 2 electrons. S subshell have 2 electrons, so their orbital will be 1, and it is represented as this box. And P subshell have 6 electrons, so divide the 6 by 2, so it have 3 orbitals, and it is represented by 3 boxes which have same energy level. D subshell can accommodate 10 electrons, so it have 5 orbitals, so there are 5 boxes which have same energy. And at last F subshell have 14 electrons, and it have 7 orbital that can be represented by 7 boxes which also have same energy. The total number of nucleons is equal to the mass number of the atom. Nucleons is number of protons, number of neutrons, and it is also known as the mass number. Now we will see the valency. Valency of an element is the combining capacity of the atom of element with the atom of the same or different elements. And the combining capacity is explained in terms of their tendency to attain a fulfilled outermost shell, which is octet or duplet. So valence is nothing but a combining capacity of an element with other element or same element. The number of electrons gained, lost or contributed by sharing by an atom of the element gives us directly the combining capacity or valency of the element. The valency of element is determined by the number of valence electron in an atom of the element. And you know the valence electron, what is? The electrons present in outermost shell of any atom is known as valence electrons, and we can find out the valency of element by knowing the valence electrons. So here two cases. First one, valency of element will be equal to number of valence electrons. Condition is that when valence electrons are 1 to 4. And second one is that valency of element can be determined by the formula 8 minus number of valence electron when valence electrons are 5 to 8. So we will see some example to find out the valency of any atom. First, for we want to find out the valency for sodium. You know that atomic number of sodium is 11, so its configuration will be 2, 8, 1. And the outermost electron in M shell will be 1. So valency of sodium atom will be 1 according to formula number 1. Because valency of element which have number of valence electron 1 to 4 have the same. So for sodium valency will be 1. Means we can say sodium will combine with other element by contribution only 1 electron. Another example is magnesium. Atomic number is 12. Configuration will be 2, 8, 2. So here valence electrons are 2. So valency will be 2. If you want to find out the valency of nitrogen, the atomic number of nitrogen is 7 and configuration will be 2, 5. Now valency will be 8 minus number of valence electron, that is 5. So valency will be 3. For chlorine, atomic number is 17 and electronic configuration will be 2, 8, 7. So valency will be 8 minus valence electron, that is 7. So it will be 1. So we can find out the valency of elements by using that formula. But there are some elements which show variable valency. For example, copper, it shows +2 and +1 compounds. The compound which are have +2 are known as cupric, and which have +1 are known as cuprous. Like that, iron also have two type of valency, Fe+2 and Fe+3. Tin also have two types of valencies, Sn+2, Sn+4, etc. Now, what is atomic number? Atomic number is represented by capital Z. The number of protons in the nucleus of an atom of a given element is called as atomic number of that element. So here we can define atomic number. The number of protons in the nucleus of an atom of a given element is known as atomic number of that element. For example, if you want to find out the atomic number of sodium, then we know that sodium have 11 protons in the nucleus, so atomic number of sodium will be 11. So we can also say atomic number is the number of protons present in the atom of element, simply denoted by capital Z. So here atomic number will be equal to number of protons equal to number of electrons in neutral atom. Atomic number can also be found out by number of protons in an ion. In an ion we cannot find out the number of electrons will be equal to number of protons, because in ions electrons can be loosed or gained, so their electrons will vary and the atom will not be neutral. So in case of ion, the atomic number is nothing but number of protons present in the nucleus. Any symbol can be represented by A, Z and A. Here Z is atomic number and A is mass number. Atomic number you have seen. Next we will see mass number, represented by capital A. The mass number is the sum of the number of protons and number of neutrons present in an atom. Sum of protons and neutrons present in nucleus. That is mass number. So we can say A will be equal to number of protons plus number of neutrons. Examples. Suppose here is written aluminium 1327, and you have to find out the number of protons, electrons, neutrons, mass number and the atomic number. First of all Z, then P, E and A. If you know that the left subscript 13 is denote the atomic number, that is 13, and if atomic number are 13, then obviously number of protons will be 13, and we know that aluminum here is the neutral atom, so electrons will also be 13, and there is 27, it is situated in the left superscript, it is denote the mass number of aluminum, it is 27, and neutron will be mass number minus number of protons, that is 27 minus 13 will be equal to 14. So in 13 aluminum 27 element, number of protons will be 13, atomic number is 13, number of protons are 13, number of electrons are 13, number of neutrons are 14, and the mass number is 27. We will see another example here. Suppose an element given X 56, 118. Now find out Z, A and P and E. Here we can see 56 in the left subscript, this denotes to atomic number, that is 56, and 118 denotes to mass number, that is A is 118. And atomic number is equal to number of protons in any neutral atom, so it is 56, and electrons are also 56, and neutrons will be 118 minus 56, that is 62. Next we see isotope. The isotope of an element have the same atomic number but different atomic masses. The isotopes have the same number of protons and electrons. The difference in their masses is due to the presence of different number of neutrons. Suppose there is a hydrogen gas in a container. We have hydrogen gas in a container. Now all these dots denote to hydrogen molecule, that is H2. And we know that H2 is nothing but made up of two hydrogen atoms. Now there are some dots in this container which have some different properties than other dots, and these dots have different masses then other dots, and these are isotopes. So what is the difference between this hydrogen and the other hydrogens? That is known as isotopes. So isotopes of an element we can define here. Isotopes of an element have same number of protons but different number of neutrons, or we can say different number of nucleons, or we can say different mass number, are known as isotopes. Here we will see isotopes of hydrogen. The first isotope of hydrogen was found protium, denoted by 1H1. Second one is deuterium, 1D2, and third one is tritium, 1D3. Here we will see atomic number, number of protons, number of electrons, number of neutrons, and finally mass number. Here you can count the atomic number in 1H1 is 1, for 1D2 is also 1, and for 1D1 is also 1. Number of proton is 1, 1, and 1. And all these three are neutral, so number of electrons will be same. Now mass number, in first case is 1, in second one is 2, and third one is 3. So number of neutrons we can count here. 1 minus 1 equal to 0, 2 minus 1 equal to 1, and 3 minus 1 equal to 2. So here you can see there is difference in only of number of neutrons in all these three atoms, but the protons are same, like that. Now we can compare here. In the first one, that is 1H1, number of protons are 1 and number of neutrons are 0. In case of 1D2, number of protons are 1 but number of neutrons is also 1. In case of tritium, number of protons is 1 and number of neutrons are 2. So there is difference of neutrons, so mass will also change because number of neutrons are changing. The first one is denoted by, is known as protium. The second one is known as deuterium, and the last one is known as tritium. And obviously the heaviest of these three isotopes will be tritium because its mass number is highest.